got lousy Wi-Fi, and it just would not load from there, but it finally loaded last night. Okay. So we'll start from current slide. Okay. So here's example 5. It says find the indefinite integral. So that's all it was. I was thinking there was a big problem to this one. How would you integrate that?
Take a derivative and a derivative.
Second, antiderivative.
Yes, for an antiderivative.
Okay, of the first, and what do you get?
That would be t squared over 2
I, perfect.
plus 3 squared over 2
3t. There's no squared in there. There's no t in the second term. So the antiderivative of 3 is,
right.
yeah, 3t j plus some constant vector. Oh, oops. I put a hat over it. I didn't need to. Some constant vector c. And you could say c1i plus c2j or something like that, but it's just some constant vector c in 2 dimensions. It has an I component and a j component. So let's see if that's how they do it. They put a capital C. I don't know why. There's no real reason. But t squared over 2i plus 3tj plus c. But c is a vector in 2 dimensions. All right?
So
Yes.
a little bit time to know this point. Just like talk through that backwards again, just say why that's the antiderivative.
Okay. You could do this. You could have split this into the integral of ti dt plus the integral of 3j dt, right? And you did this one right. That would be t squared over 2i, right? Plus, you could break this down into 3 times the integral of j dt, right? But j really isn't anything, so you could pull that out too. Plus 3, I'm going to pull it out on the other side over there, so you don't think of it as a constant, you know, because you're not really integrating that. What's the integral of dt? It's just t. Yeah. So that's why it's 3t. Is that what you needed?
Yes,
Yeah. Right. And then both of those integrals have constants, one in I and one in j, but that's just the constant c. You know. Okay. C1i plus c2j.
And the reason that we stopped using x is just because you might get confused as you might think it's a cross.
Oh, I didn't think of that. Well, a couple reasons. Number one, as my one of the first slides in my Cal 1 class this morning, once you start integrating, especially if you're doing definite integrals, then the thing in there is sort of a dummy variable anyway. Doesn't matter what it is. It could have been an x, but you're right. You think of x as being a component in the I direction. You don't think of x being a component in the j direction. So if that was confusing to you, then it's better to use t. But then on the other hand, if this is talking about a direction, you know, a vector that's going in a given direction, not just some abstract vector, then usually time is an independent variable, so we use t. Doesn't have to be. It could be something abstract and they just use t out of nowhere. But if you're doing displacement, velocities, accelerations, they all depend on time, so that would be the independent variable. And usually what we do use in the parametric, often we use it as a parametric equation. The dummy variable there. So that's what we got. Let's see how they did it. Probably pretty much the same way. Yeah, they just wrote it down, integrating on component by component basis. The integral of this, t squared over 2i, this the integral of 3 t dt would be 3t j, and then some constant vector in with an I and or a j component. Either one of those could be 0, but yeah, generally it would be. So then example 6, they don't show. So let's go back and do example 6. Evaluate this integral. This is a definite integral from 0 to 1, r of t dt. Okay, where r, and by the way, back on the issue of the variable, these correspond to values of t. Okay, so it's from t going from 0 to 1. Not r going from 0 to 1, but t going from 0 to 1. Okay? That would be the integral from 0 to 1 of, and if your r vector was the cube root of ti, the cube root of tt, that makes no sense. Okay, cube root of ti plus 1 over t plus 1j plus e to the minus tk, okay, dt. All right, well, that's what we're supposed to integrate. All right, now how would you proceed? Okay. Number 1, I'm going to notice I didn't jump right into doing an antiderivative, I wrote an integral again. The reason I did that, I don't like ever to try to integrate a radical or differentiate a radical. I like to put them in exponential notation. So let's do that first. That would be t to the 1/3 I plus. Now this one, you may or may not do this. This would be all right the way it's done, but you might want to do that as a t plus 1 to the minus 1 j, if that's helpful to you. Okay? And I don't think there's much we can do with the k part, so we'll just do e to the minus t k dt. Now let's integrate. It's the antiderivative of t to the 1/3.
The 4/3 t to the 4/3.
Okay, divided by 4/3, which is the same as times 3/4. You know, you divide by the exponent, and if it's fractional form, go on and invert and multiply. A little bit easier. That would be in the I direction. Now, you could also do this. We can also evaluate the limits component by component if you wanted to, or you can do them at the end. You have a preference?
Do it at the end, probably.
Okay, we'll just wait and do it at the end. Okay, so we'll put a big bracket here. And now, I rewrote this one this way. It wasn't really necessary, but I found it easier to do an antiderivative of this. What would this be?
Well, it ended up being minus.
Okay. Well, if you were to increase this by 1 like you did this, that would give you to the 0th power, but then you would need to divide by 0, which we don't usually like to do.
Right.
So this isn't a power function. It looks close, but power function only works where the power is not -1. What is the antiderivative if it is -1? It might have been easier to look at it this way. So, I mean, they're the same thing. If that had just been 1 over t, what would the antiderivative be?
Log.
Log, exactly. So this is ln, the natural log of t plus 1. Okay. Now, there is no chain rule part to do with that because the derivative of t is just 1, so that would be okay. Now, but okay. If this were an indefinite integral and we didn't have limits here, we would be required to put that in absolute values. But since we do have limits, and between 0 and 1, this thing is always positive. So we don't need the absolute values. Parentheses will do fine. That will be our J component. And how about the next part?
If I remember correctly, that should just be e to the plus e to the negative t. Right?
No. Just minus t. Because the antiderivative of e to the t is e to the t. It's the same thing, except for a chain rule part that then changes to plus or minus.
Yes.
Okay. Make sense?
Yes, sir.
Okay. Now probably, yeah. And then we'll evaluate this from 0 to 1. Now be careful, because a lot of times we are used to, or I'm used to anyway, so I shouldn't speak for you. If that's a 0 on the bottom, to say, oh, that was going to be 0, and forget about it. Not so. It is if it's a power thing. Usually that is 0. But if it's not a power, we have a log and an exponent that are not powers. So we need to evaluate each one of these individually at both places. So that's one reason. May have been a little bit better to break up the components, but as long as you remember to do the components together, you're fine. So on the first one, when you plug in 1 for t, what do you get?
1.
Yeah, t to the 1 to the 4/3 is 1, but then you got a coefficient 3/4 I. And when you put in the minus 0, it's 0. Okay, so that's it. Okay, that's the first part. Plus, now what do you do if you plug in a 1 for this one?
I'm looking at the totally wrong thing here.
What's that?
I'm writing in the wrong.
Oh, I see. Well, right in the right place here. Okay, all right.
And then, so that would be log of 2.
Log of 2 minus
minus
log of 1. right? Okay, you got to do the whole thing. Log of 2 minus log of 1, but what is log of 1?
0.
0, okay, so that's 0. So this one also has a 0 component, but not for the reason the other one did. Okay, so that's just log 2j minus
e to the negative 1.
okay. I'm going to open a parentheses here. Maybe I shouldn't. Yeah, I think I will. E to minus 1, okay? And then you're going to have a minus for the other part, e to the 0. What's e to the 0? 1, okay. Okay. All right. Now, everything's pretty hunky-dory there, except I like to clean up that last one a little bit. So that would be 3/4 I plus log 2j. I don't know if I need parentheses there. I'll just put them in. Okay. I guess part of the reason is so you don't think it's log of 2j. It's not. It's log 2 of j, times j. Now, here's what I want to do on the last part. And there's no special reason, but I just like leading off with a positive. So that would be plus 1 minus 1 over e, or e to the minus 1. Okay. Okay. There's no big reason. I could have left it minus e to the minus 1, but I just changed the two minuses to a plus, and that made the e to the minus 1 minus. So either e to the minus 1 or 1 over e, it doesn't really matter. My writing really stinks, but let's see if I can clean that up a little bit. Cleaned it up too much, but okay. And that, by the way, is how they wrote theirs. That's surprising. I usually don't agree with the book exactly on how to present the answer. And they even put the log 2 in parentheses and the 1 minus 1 over e. Okay, perfect. Now, that was example 6, which they don't show in the thing. Neither they do example 7. So, any questions on 6? Okay, so let's go to 7. And I know that sounds terrible on the videos because I've heard myself do it a few times, but I just get so clogged up I can't breathe hardly. Find the antiderivative of r prime of t equals to cosine 2ti minus 2 sine t j plus 1 over 1 plus t squared k. Okay, find the antiderivative of that. Okay. Oh, that satisfies. I left off this. R of 0 is equal to 3i minus 2j plus k. Okay. Okay. Well, what is the antiderivative of a derivative? Okay.
Just the equation.
It's the function r. Okay. So we're undoing that. But when they say antiderivative, usually that doesn't mean a definite integral. That means indefinite integral. So basically we're going to take a integrate this thing, but not with any limits. So that's going to be the integral of cosine 2ti minus 2 sine t j plus 1 over 1 plus t squared k dt. Okay? I hope I wrote it right. I can't talk. So, what's the, goodness gracious, what's the antiderivative of cosine 2t?
Negative sign?
Okay, if you were taking a derivative, that would be a negative. Taking the antiderivative, though, is a positive. Sine of 2t I, but you have something else there. Sort of a reverse chain rule type thing, right? Because it's not sine of t, it's sine of 2t.
Oh, so it'd be 2 sine?
So, no, if you're taking a derivative, it would be 2. Taking the antiderivative, you divide, not multiply. So that would be over 2. Okay? Now, I don't know I think that it's probably better to do individual C's here. In my mind it is. So let's do C1, C2, and C3 here, plus C1, okay? So that would be your I component, okay, minus, or maybe not,
minus, no, so now it would actually be a plus.
Yeah, that would be a plus because the antiderivative of sine is minus cosine, okay? So that would change that to plus 2 cosine t plus C2 j. You okay with me doing that? Okay. I think it'll be easier in the next step to have them individualized like this, okay? Most of the time, I just write down a vector C, okay? But this time, I'm doing component by component, okay? Now, the third part. SpaghettiOs. Any memory on this one?
Would not be a lot of 1 plus.
It would be if there was a 2t in the numerator, but there's not. Or even a t somewhere in the numerator. There's not. This is one of those I always get a little confused whether to call it, yeah, it's a trig function, okay? Not a trig integration, but a trig function, okay? And you basically almost have to do it is a substitution of sorts, just not like our normal ones, okay? And you remember what?
We want to do, do we need to do a substitution?
Yeah, it's going to be a trig substitution.
So U would equal 1 plus T.
Okay. Now, this one you go the other way. You say The trig substitution you do another way. You let t, the thing that's here, be a trig function. Now, which trig function would you want it to be? Hint. Trig functions that have squares in them are what identities come to mind?
Sine squared plus.
Okay, the Pythagorean identities. Okay. Now, if this were 1 minus t squared, I would think in terms of sine, because 1 minus sine squared is cosine squared, and things are going to work out okay. This is a 1 plus t squared. Now, which of your Pythagorean identities has a trig function squared with a plus on it?
Is it is it 1 plus secant squared or 1 plus tangent squared?
1 plus tangent squared. Yeah. Okay. Secant squared is 1 plus tangent squared.
Yes.
So that's going to be what and because you don't have any other letters or numbers in here, it's just going to be a straight tangent. I usually like to use theta, but you can use any other dummy variable you want to. Let t equal tangent theta. Okay. Then t squared, of course, will be tangent squared theta, right? And 1 plus t squared would be 1 plus tangent squared theta, right? And what is 1 plus tangent squared theta? That's secant squared theta. So 1 plus tangent squared theta is equal to secant squared theta. All right. So there we've got that carried as far as we can. But we also need to do a dt, right? So let's do what dt is. What is the derivative of tangent?
Derivative of tangent is 1 over secant?
No, it's just secant squared.
Oh.
Derivative of tangent is secant squared, which is d theta. Okay, you always need the d's with the d, you know. Why suddenly my back has just started itching. I think pollen and stuff irritates my skin, and I just want to get up against a tree and rub like a cow, you know, or something like that. Okay. Now, what we have is a pretty interesting situation then. If we just look at the integral of this term, dt, okay, our numerator is a dt, and that's secant squared d theta, and our denominator is 1 plus t squared, which is secant squared theta. So this is secant squared theta over secant squared theta, which is 1. So what we have is just the d theta, okay, because you went from d theta to dt's. dt's to d theta's up there. So that would just be the antiderivative of theta k. Okay? Now, it's not in terms of but the antiderivative of, no, I'm sorry. Let me back off a little bit. Okay. All right. Let's actually do this. This would be, all right. I'm going to rewrite this as the integral, and I probably should have to begin with, of 1 over 1 plus t squared dt, and that's going to be the k term, right? And we just did that. The dt is secant squared theta, so it's the integral of secant squared theta d theta over 1 plus tangent squared, which is secant squared theta. So these go to 1. This is all times k. So the antiderivative of d theta is just theta k. And that's why I wrote it down, but I was afraid that I was leaving out too much. Okay. Oh. Yuck. Get out of there. Okay. I forgot to do my constant. Well, there we go. No. Getting in a hurry and yeah, okay. Theta plus C3 K. All right. Okay with that?
Yes, sir.
All right. Now, since we don't have limits on it, what we do know from here, when t is equal to 0, your r is 3i plus minus 2j plus k. So we're going to go in and plug in a 0 here. So when t is equal to 0, what does this give you? What is sine of 0?
0.
Okay, so this just gives you C1i plus, now when t is 0, what is cosine? 1. So this will be 2 plus C2j, right? Plus, now, when theta, okay, I guess we need to do this. If t is equal to tangent theta, then theta is equal to inverse tangent of t, right? Okay, so we need to go back and do this. This will be inverse tangent of t plus C3. Oops. Let me do this on the line above. It's going to come down here in a minute. But instead of theta here, we're going to put inverse tangent of t. Okay, that's sort of ugly, but you got what it is. Okay. Now, so when you put in t equals 0, what's the inverse tangent of 0? 0. Because remember, the tangent function goes through 0 just like sine, because it's sine over cosine. Okay? So, inverse of 0. So that would be 0 plus C3. And we don't need the parentheses anymore. C3 K. Okay. So, we know this should be equal, when t is equal to 0, our r of 0, should be 3i minus 2j plus k. So, that means that the C1 must be 3, right? Okay, so our... can I erase my stuff at the top?
Yes, sir.
Okay. This is where I'll write my final answer. Okay. Feels like Jeopardy, doesn't it? Okay. Okay. Almost got it all erased. All right. Goodness gracious, my eyes are itching too. It's got to be the pollen. All that rain should have washed most of it out of the air, but okay. So that makes the C1 to be 3. So we go back to our formula here, and our final answer is sine of 2t over 2. That 2t shouldn't be elevated. It just somehow got a plus 3, right? That was our C1. So this is our I plus 2 cosine t plus C2. Now, we hadn't determined what C2 is yet. We have here that 2 plus C2 is equal to negative 2, right? 2 plus C2, that's the left-hand side, is equal to negative 2. So if you subtract 2 from both sides, that gives you C2 is equal to negative 4, right? So that'd be 2 cosine t minus 4 j plus.
And where did the minus 4 come from?
All right. We saw here when we plugged in, this was our expression that we got from integrating that, right?
Yes.
Okay. And we plugged in t is equal to 0 here. And that gave us just C1I plus, and this gave us a 1, you told me.
Yes, sir.
And 2 times 1 is 2 plus C2J plus, and that was a 0, C3K. All right, but we know this thing at t equals 0 should equal this thing. So that makes us C1 equal to 3. 2 plus C2 is equal to minus 2, right? Well, 2 plus C1, there it is. 2 plus C2 is equal to minus 2. Subtract 2 from both sides, you get C2 equal to minus 4. So that's what we plug back in to here. So then you get plus 2 cosine t minus 4 j plus inverse tangent, that's where I was. Oh man, that hurts. Inverse tangent of t plus C3 is equal to 1. Okay. Now, you can write it like that, or you could have written it this way. Sine of 2t over 2I plus 2 cosine t j plus inverse tangent of t k. I don't know if it's helpful to put those in parentheses or not. It may be, just so it's a little easier to read, especially if I don't have the K looking so ugly here. There, it looks better. And then you could just do plus the vector, and this vector was then, I'm just going to write it in vector notation to make it easier, 3 comma minus 4 comma 1. Okay. You could have done it that way, either written them as one vector up there or as a variable vector plus a constant vector here. Yeah, just pulling out the I, J, and K and doing separately. I don't know how the book left it. Let's see if we can find that out. Oh, they left it in the first form. 1/2 sine of 2t, that's basically what I have, plus 3i, plus 2 cosine t minus 4j, plus arctangent, they write arctangent rather than inverse tangent of t plus 1k. Good deal. Make sense? Okay. And that does finish 12.2. And 12.2, homework exercises will be any of the odds, 3 through 9. They're all at Calc Chat, 5's at Calc View. Do any of the odds 11 through 17. They're all at Calc Chat. Do either 19 or 21 or both. They're both at Calc Chat. Either 23 or 25 or both. They're both at Calc Chat, but 23's at Calc View. Any of the odds 27 to 33. They're all at Calc Chat. 27's at Calc View. All right. again, I think it's pollen. All this drainage is driving me nuts. 35 is both at CalcChat or CalcView, both at and. 37 is at CalcChat alone. Any of the odds 39 to 45, they're all at CalcChat. 41's at CalcView. Any of the odds 47 to 51, they're all at CalcChat. 47's at CalcView. 53 through 57, they're all at CalcChat. 53's at CalcView. 59's are exploring concepts. You can explore that if you'd like. Excuse me. Any of the odds 61 to 67, they're all at CalcChat. Either 69 or 71, they're both at CalcChat. There's a true false 73 or 75, they're at CalcChat. And that's it. Okay, good. Thought there was another page up. That's good. All right. Any questions on 12.2? All right. None? Or are there? Okay. All right, let's move on to 12.3. All right. I'm hoping I don't have to go clear my head. I'm just feeling more and more congested, but let's see if we can make it through. How much longer we got? Ooh, a long time, isn't it? About 40 minutes. Yeah, a little bit longer. So let's get started with the current slide. And if you don't mind, this might not be a bad place. Let me just pause it here, go down and clear my... And kind of another issue here, I'm hoping this is allergies, because my wife last week, almost all week long, was tied up with a big international meeting that was in Birmingham, and she was on the organizing committee and stuff. So for weeks now, she's been working almost nonstop, getting everything, all the things in line, and to do an international meeting. And it was a big deal, and she was there. She didn't even come home. She stayed at they had a complimentary room because she was on the organizing committee, so she had to stay there just to make sure everything was working right and stuff like that. And she worked herself to death. And someone said right near the end of the conference to she and another woman who had been on, she said, "Don't be surprised if y'all get sick, because you've been around all these people, you've been working so hard, and you've worn yourself down. Don't be surprised." And sure enough, the next day she had a terrible sore throat, and then she's been coughing, and she said it hurts to do anything because she's coughed so much, her sides are sore, and sneezing, anything just is excruciating. She can't sleep, has to sleep sitting up, because if she lays down. So that's what I'm hoping, that this is that, stuff outside, not I'm catching her cold. So that's why I'm trying to keep fluids and stuff like that in to keep everything loose. But anyway, I didn't need to record all that, but I did. So we're still in Chapter 12, vector value functions. 12.3 is velocity and acceleration, which in a sense we've already done, but we haven't called them that. Okay? We'll describe, I'll even turn on the projector again. So you didn't get to see the pretty pictures there. I'll let you see them. I was looking at them. Well, maybe the projector will come on. There it comes. There's Chapter 4, vector value functions, and Chapter 12, vector value functions, 4.3, velocity and acceleration. So the first objective is to describe the velocity and acceleration associated with the vector value function. And we'll use a vector value function to analyze projectile motion. All right. As an object moves along a curve in a plane, the coordinates x and y of the center of mass are each functions of the time t. Like I said when you asked before something about T, or I said something about T, no, I think you'd ask it. And usually the reason you gave was a good one, but the other reason, usually it's a function of time. If you're talking about motion, it's usually a function of time. Rather than using the letters F and G to represent these two functions, it's convenient to write x is equal to x of t and y is equal to y of t, okay? Which is a little bit, pure mathematicians probably wouldn't care for this notation, but this is a pretty good mathematician here, and he doesn't seem to mind, so we'll go with that. So the position function r of t takes on this form: r of t is equal to x of ti plus y of tj. And if you think about it, we did that well back there. We did call it a position vector at the time, but that's exactly what this is. This is a scalar function of time, and that's a scalar function of time. So the x and the y functions, are acting independently of each other, and that gives you the position vector. This is in a plane because there's only two components of it. To find the velocity and acceleration vectors at a given time t, consider a point q, which is x of t plus delta t, some short time after t. That's its x component, and its y component is y of t plus delta t. That is approaching the point P, x of t, y of t, along a curve given by this. So it's kind of backwards the way they're saying it, but it's fine. Here's the point Q, somewhere way off there. The delta t is pretty significant here, because here's your t for P, and here's your t plus delta t for Q. So it's quite a bit further. I'm sorry, I pointed at the x-axis. The t is moving along pretty well there. So if you let the delta t get less and less and less, as you get back here, there is your velocity vector at time t. Because you've taken the slope, the derivative, dr dt, but the dr dt is dx dt. You take the derivative of both the x and y components, okay? And as delta t approaches zero, the delta r over delta t approaches the velocity vector, which is your tangent vector there. So you see the delta t is getting less and less and less, and the secant vector is approaching the tangent vector, just like we did way back, okay? Cal 1. All right, as delta t approaches zero, the direction of the vector PQ, denoted by delta r, and that was the other thing. This vector P to Q is your delta r, because this is your r vector here. Here is r of t plus delta t. So the difference between this one and this one is that vector here. Okay, so this one plus this one equals that. So that's the difference between these two. And so that's your delta r, which is also your vector PQ. Okay, approaches the direction of motion at time t. So the delta r is your difference of r of delta t, r of t plus delta t minus r of t. And when you divide that delta r by delta t, you get your derivative, which is, of course, that. When that limit exists, it's defined as the velocity vector or the tangent vector to the curve at point P. Velocity of the point or tangent to the point at the point to the curve. Right? Notice that this is the same limit used to define r prime of t, so the direction r prime of t gives a direction of motion at time t. Moreover, the magnitude of that velocity vector, magnitude of r prime of t, is the magnitude of these two, and there's Charles. Okay. Well, there you are. At honors and awards ceremony last time, congratulations, that's last Thursday, You are the Charles Hendricks that, okay. But this guy went up there, same guy went up there, I said, there's either two Charles Hendrickses or he's just being a sub. Well, a little bit later, he went up as somebody else too, and the guy next to him said, he must be a sub. Okay, so I said, either we got two really good Charles Hendricks here, or that guy's an imposter. No, it's...
I was on a project site in St. Clair County, and I couldn't, I wasn't able to make it.
Yeah, but congratulations anyway, even though you
What
couldn't
was
be
the
there.
award?
Delta Signal Scholarship.
Yeah. Yeah, I can't remember. You had a couple, didn't you?
I applied for a few, but I know I got the award for that one.
For what?
For that one.
For which?
Delta Signal, I think.
Oh, yeah, okay. Let's see if I can find you. Yeah, the first one was the Delta Omega Scholarship, the Delta Sigma Theta Sorority and Omega Psi Phi Fraternity. Yeah, you received that one, you and Francesca Blair. And then I thought there was another one.
Was it for the Kappa?
It may have, yeah, it may have been that. Let's see. My eyes aren't focusing well, so I may be missing it.
Yeah, I know I got a call about Delta. I applied for the other one, but I haven't heard anything back on it.
Yeah, you got that one. And it may be it's one they didn't print the name here, they just called it out. But I thought there was, I thought I saw your name in here twice. But it was a long ceremony. I'm sorry, my first class there was also a recipient, but she came in late too, and I forgot to mention it. And she came in. Yeah, I don't see it. So it may have been one that was just announced without printing the book. In the book. What is your major?
Mechanical engineering.
Okay. Pretty sure it wasn't that one because I know the guy who got that one. So it probably was just one that the name wasn't printed, that they just announced at the program. Because I know the guy went up there twice as Charles Hendricks. And then so that could have meant he was still Charles Hendricks. But then when he showed up a third time for another award, I said, ha! And the guy next to me said,
it might have
nope.
been for the Kappa. I applied for that.
Yeah, it may be, because yeah, the Kappa Alpha, yeah, there it is. Kappa Alpha Psi Fraternity Book Award. It doesn't have a name by it, so they may have just announced it. And it seems like it was real close to the other one, and that was the, I think he actually skipped that and went down later and then went back and picked it up. So yeah, I think that was it.
That works out.
And here is Daniel. But congratulations.
Thank you. We just went there all.
Yeah, it was at the Honors and Awards. He got a couple of awards there. I don't remember. I can't remember everybody who did, but the reason I remembered him is I saw Charles Hendricks in the program. They announced Charles Hendricks, and some other guy came up. I said, either we got two Charles Hendrickses who do pretty well, or he's an imposter. And then later, the same guy went up for somebody else. So he was just picking up awards for them, just so there wouldn't be a blank nobody there. So it was just a sub.
I had to work. I couldn't make it.
Yeah. So anyway, that's why I was giving him a hard time. Somebody else was impostoring you. Okay. All right. What we're doing is velocity and acceleration. We're in section 12.3. And this is on page, kind of the bottom of page 836. We'll soon be on 837. Note that this is the same limit. Okay, we're talking about r prime. And the magnitude of r prime would then be the magnitude of x prime of t I plus y prime of tj, which is the square root of x prime of t plus y prime of t. And by the way, that happens to be the speed. If the other is the velocity, magnitude of velocity is the speed. Speed doesn't have a direction associated with it. Velocity does. Velocity has i's and j's. Speed is just the magnitude of velocity in whatever direction it's going. All right. Similar to how r prime is used to find velocity, you can use r double prime to find acceleration, as indicated in the following definitions. If x and y are twice differentiable functions of t, and r is a vector value function given by r of t is equal to x of ti plus y of tj, then the velocity vector, acceleration vector, and the speed at time t are given as follows. The velocity is v of t is r prime of t, which is r x prime of ti plus y prime of tj. When you're taking derivatives of vector value functions, you take them derivatives component by component. The acceleration would be the a of t, and by the way, these are all vectors as well, which is second derivative of r of t, and that would be second derivative of x of t, I, plus second derivative of y of t, j. And the speed is the magnitude of the velocity vector, which is the magnitude of r prime, which is the square root of x prime squared plus y prime squared. Scalar value, speed, no direction associated with speed. All right, for motion along a space curve where you have three dimensions, all the definitions are very similar. It's just that r of t is now x of t I plus y of t j plus z of t k. Three dimensions here, and you have the velocity vector being x prime of ti, y prime of tj plus z prime z of tk. Acceleration, the second derivative of the displacement vector, which is r double prime of t I plus y double prime of tj plus z double prime of tk, and the speed would then be the magnitude of the velocity vector, which is the square root of x prime squared plus y prime squared plus z prime squared. Scalar quantity, no direction associated with it. All right, make sense? All right, here's example 1 then. Find the velocity vector, the speed, and the acceleration vector for the particle that moves along the plane curve C described by this displacement vector. Let me get my pen set up. So your velocity vector v of t is going to be your r prime of t, which would be what? Take a derivative of that. Anybody? Anybody?
Negative 2 sine. Negative 2 cosine.
Okay, now we're taking derivatives this time. Derivative of sine is positive of cosine. Okay?
Keep going backwards.
Yeah. So this will be?
2 cosine.
Okay, you can start it that way. 2 cosine of t over 2 I. But you got a chain rule with the t over 2.
So you have to divide by 2.
Divide by 2, so that goes to 1. Okay? So cosine t over 2I
And
now it'll be a negative.
Minus 2 sine
2 sine t over 2 j, but you also have a chain rule with that one, so the 2's. So that'd be over 2, so the 2's go out there too. So you have cosine t over 2i minus sine t over 2j. That's your velocity function. Okay? Now the speed. So that's the A part. The B part is the speed. And we don't really have a symbol we call for it. We just usually will say the magnitude of velocity function, which is magnitude of r prime 2, but I'm just going to leave that out. What would that be?
Is the square root
Of?
Cosine squared
Right.
t over 2
No, you don't need i's and j's in this because velocity, speed is a scalar quantity. When you do the square root, you just do the components.
then minus sine t.
Yeah. But you're squaring it, so when you square a minus, it becomes a plus. Sine squared t over 2. Okay. Which, anyone notice what that might be?
1.
Yep, that's just 1. Strange but true. Okay. Your speed of that, because it all in terms of sine and cosine is just 1. Okay. The C part, the acceleration part. Don't need the speed for this, but you do need the velocity, so your acceleration vector as a function of t is, by the way, the first derivative of your velocity function as a velocity vector as a function of t, which is also your second derivative of your displacement function as vector as a function of t. Okay, so go back to this one, and what is your derivative? What is your acceleration vector?
This will be negative sine
Of t over 2 I with chain rule component.
Divided by 2.
Yeah, divided by 2, or 1/2, multiplied by 1/2, right? Okay, next.
And plus, well, it'd still be negative, wouldn't it?
Yeah, it stays negative.
Cosine t over 2 divided by 2.
Divided by 2. Okay, or 1/2 of that. Okay, now, just a couple of things to note here. I don't know if you realize this or not, but this position function here is circular. In a plane, that's going to be a circle. Okay, centered at the origin, that's going to be a circle. And your velocity vector, just by the nature of the values here, is always going to be, the magnitude of it, the speed is always going to be 1, just because of the way the numbers pan out. The acceleration vector, notice it, it's exactly the opposite of your displacement vector, with a factor of 4 involved, okay, 1/4 the thing, but in exactly the opposite directions. One, the acceleration is minus sign, whereas the displacement vector is plus sign. On the I component, minus cosine on the j component, whereas that was positive j. Yeah, different coefficients, you know, 1/2s and 2s, but still in the opposite direction. Which means that, so here's the origin. Let me use the board here. I won't get out of range of my microphone here. But if this is your it's a circular motion about the origin here. Your velocity vector is always going to be same magnitude, and it happens to be magnitude of 1 all the way around. Your acceleration vector, your displacement vector is this way. Positive x, positive y, so it's pointing in that way. Your acceleration vector is pointing exactly opposite. Over here, it would be negative in x and positive in y, and yet, so it would be pointing this way, and the acceleration going always toward the center. With circular motion, which is what we have here, we have a centripetal acceleration, always pulling toward the center of the circle, which you run into in physics as well. Okay? So that, I think, is all it called for. Let's see what they've got. They've got the velocity vector being cosine t over 2i minus sine t over 2j, correct? The speed, 1, same as we got, square root of cosine squared t over 2 plus sine squared t over 2, 1. And the acceleration vector is r double prime is negative 1/2 sine t over 2i minus 1/2 cosine t over 2j. All right, good deal. And then they show the picture in your, let's see if they show it. Hold on. All right, is it getting close to time to leave, or you just got to leave? Okay, we got another 10 minutes or so. Okay, let me clear, oops, that's not what I wanted. Clear my writing so we can see what they do. And there's their velocity vector, the first derivative of the displacement vector. The magnitude of that is your speed, which in this case happens to be 1 exactly. At any time is 1. And the directions are changing, but the magnitudes are the same. And your acceleration vector is minus 1/2 of sine t over 2 minus cosine, 1/2 of cosine t over 2j. Whoa, they didn't show the thing. But in your book, they show what I was trying to finger point at the board there. Here's your motion. I can hold the book up here. Circular motion centered about the origin. The displacement vector always pushing this way, but your magnitude of your velocity is constant here, and it happens to be a constant of 1, and your acceleration vector always pointing in the opposite direction of your displacement vector, and it's a center seeking because it's circular motion. All right. Now, I think we're ready for example 2, but they're jumping to projectile motion, which is a couple pages off. So let's go back and do example 2. Sketch the path of an object moving along the plane curve given by r of t is equal to t squared minus 4i plus tj. All right. Now, I can't remember if both of you have been here since I started the vector value function in this chapter, but just to remind you, any old regular vector, because I can't write bold like they do there, I put an arrow over it. Any old regular vector. Okay. If it happens to be a unit vector that we know is a unit vector, I put a caret over the top, the steep roof over the top, just to indicate it's a unit vector like this and this. They just do bold for all of them, but I like to specify, if I know it's a unit vector, indicate that by the caret top, whereas any old vector may not be a unit vector, then it just says an arrow, because I can't write bold. Okay? There's our position vector. Okay. It says sketch the path of the object moving along the plane curve by that, and find the velocity and acceleration vectors when t is equal to 0 and t is equal to 2. So the first thing they say is sketch the curve. So let's sketch the curve right here. Okay? And we'll do a few points. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. Now these are x's. These are y's. Okay? But what we've got is a variable t. So Let's start the t somewhere, anywhere. Pick a t, any t. A value for t. Any value. Pick a number.
6.
6. Whew. Okay. All right. If you have 6 squared, that's 36 minus 4 is 58, is be your I component. Off scale. So let's pick one a little bit smaller. 2, okay. 2 squared is 4 minus 4 is 0. So that'll be 0i. So you go right or left. You're somewhere on the y-axis. And if you pick, you said 2, right? 2j, there you are. So there's a point on the curve. Give me another t. And this is where t is equal to 0, okay? Give me another t. 1. Okay, when t is equal to 1, this will be 1 squared is 1, minus 4 is negative 3i. Whoops, that'll be over there. Okay. Don't need one more. And then you'd have plus 1j. So there would be this point. This is when t is equal to 1. Okay? Give me another a t. Second? 3. Okay. T is equal to 3. 3 squared is 9. 9 minus 4 is 5. 1, 2, 3, 4, 5. That's the x component. And then that was 3j. So 3 would be up here. I messed something up here. I went up too far. Okay, sorry. That was 1j, okay, on that one, okay. Give me another t. This is t is equal to 3. Okay, give me another 3. Another t. Anyone will do? 4. I think that's going to be off scale, but it'd be 4 squared is 16 minus 4 is 12i. Yep, that's off scale. Come back a little less, huh? 2, is that what you said? Oh, we already did 2. Oh, I put t equals 0. That's t equal 2. Okay, that's t equal 2. T equal 1, 2, 3. Okay. Another one? What's that? 0. T is equal to 0. What would we have? Negative 4i and 0j. So there's t is equal to 0. Let's keep going. Negative 1. Okay, negative 1 would be, that would be 1 minus 4 is minus 3 minus 1. So there it would be t is equal to minus 1. Okay, let's do t is equal to minus 2. Minus 2 squared is 4 minus 4 is 0i minus 2j. There we are there. There's t is equal to minus 2. Okay, and I bet you the next one's going to be down here. Okay, what you want to bet? T is equal to minus 3. So that would be 9 minus 4 is 5. So 5j, I, 1, 2, 3, 4, 5, and minus 3j. Got it. So here is your curve. It's a good old favorite parabola. Okay? But it's going in that direction because t is increasing from negative 3 here, negative 2, negative 1, 0, positive 1, positive 2, positive 3. Increasing. So the arrow on the curve indicates the direction of increasing parameter, in this case t. Okay? There's a sketch of a curve. A pretty ugly sketch, but a sketch. That's the first part. Second part says, find the velocity and acceleration vectors when t is equal to 0 and 2. Well, we first need to find the any t. So the velocity vector is r prime at t, and what would that be? No, there's no cosine here. No sine. Not this thing.
Oh, okay.
This one here. Not that hard. Derivative of the I component is
T squared.
2t I. Derivative of t.
Plus sine t.
No, there's no sine or cosine. Not these. This one. Yeah. What's the derivative of t?
T over 2.
Okay. Okay, your exponent, which is 1, times your coefficient, which is 1. 1 times 1 is 1. And then you reduce the exponent by 1, which would be t to the 0, which is 1. So that would just be 1j. So plus j. So there is your velocity vector at any time t. Let's go on and do the acceleration vector at any time t, which is the first derivative of the velocity vector at any time t, which is the second derivative of the position vector any time t. And what's the derivative of this one? Derivative of 2t. If the derivative of t was 1, what's the derivative of 2t? Okay. Exponent 1, coefficient 2. 1 times 2 is 2. Not 2t. Drop this to the 0th power, and that's t to the 0th is 1. So this will just be 2. 2i, and then derivative of 1 is 0. So your acceleration vector is just 2i. Okay? Now, they ask for this at time t equal, okay, they want the velocity vector at time t equals 0. So we go to the velocity vector, that's this one up here, and plug in a 0. What's your velocity at time t equals 0?
0.
0i plus 1j. So that's it. Velocity vector at time t equals 0, right there. You see, you have no component of the horizontal component of velocity. The only component is upward. Because, remember, the particle is moving in this direction, and it's 1 unit up. Okay? So that's your velocity vector at time t equals 0. Let's go on and do it. It doesn't matter. Let's do velocity vector at time t equal, what was the second one? T equal 2, at 2 seconds. Well, the velocity, okay, let's plug it in. 2 times 2 is 4i plus j. Okay, there's your velocity vector. So that'd be at time t equal 2, we're right here. So your velocity is 4 units to the right and 1 unit up. So this would be the velocity there. Very shallow slope, 1 unit up for every 4 units to the right. Now I probably didn't draw mine long enough because it should be units that way, but that was just too long to do. Okay, now let's do, because there's the point where t is equal to 2. So let's now do acceleration vector at 0. What's your acceleration vector at 0? Here's the acceleration. What is it? 2i. Okay. and no J. Well, acceleration here is to there. Your acceleration is toward the center. Remember, acceleration is always center seeking, and you're accelerating inward to get this to bend like that. Okay? So that's making sense. Let's do the acceleration at time t equal 2. And what would that be? 2I. Okay? That means your acceleration here, the vertical component isn't changing, but again, it's 2I. So everywhere along here, your acceleration is 2I. Okay? It's going everywhere, accelerating in that direction. Here, that's taking around a sharp bend. Here it's this way. It's just accelerating here. Still has a component upward, but not accelerating upward, only accelerating outward, in the right-hand direction. Not acceleration up or down at all, ever. Okay? Does that make sense? What's that?
Looking over tonight.
Okay. So there is example 2. All right, I believe we're out of time, aren't we? Okay, so we'll begin next time with example 3. Let's see how many homework exercises we got covered. I think you can do any of the odds 3 through 9. They're all at Calc Chat. 3's at Calc View. You can do any of the odds 11 through 19. They're all at Calc Chat. 15's at Calc View. And we'll stop and pick up the rest of those next time. All right, good deal.
When's our last day of class on the 30th? That's our last day of class.
That sounds right. I don't know. I don't have a calendar in front of me, but it's the final exams supposed to start Tuesday, the last Tuesday in April. So the Monday before that is our last day of class. Okay, and if that's whatever day that is. Now, on that day, I'll give you your last test. That'll be your final exam, and you'll need to get that into me. Are you graduating or not?
No, sir. I'll see you again this summer for.
Okay. If you're graduating, I have to have your grades in by Friday. But if you're not graduating, it's the following Wednesday. So there's plenty of time to get them in.
So we have one more exam?
Yeah, whatever test we'll have covering this chapter 12. And if we get any past 12, it'll just be incorporated with it.
You guys have a good.
All right, we'll see you probably tomorrow. Do you have enough?
No, sir. I just see you on Monday.
Just at Monday, okay.
I see you every day.
Yeah, that's what I thought. So I'll see you tomorrow, see you on Wednesday. Okay. Good deal.
I registered for your D class this summer.